Welcome everyone. My name is Bhuvendra Singh Rawat from Department of Electronics and Communication, Section A, bearing roll number 620115, NIT Andhra Pradesh. Today I'll be discussing about Newton's method uh, for a function optimization. When we'll be dealing with complex functions or finding the maximum or a minimum point uh, can be a challenging task. So where optimization techniques comes in handy, and one such powerful technique is Newton's method. So what's the Newton method? Newton method is an iterative optimization algorithm that uses the in this method we use the first order derivative of the function to find maximum or minimum point. It is widely used technique in various fields such as physics, economics, and engineering, and many more. It has been proven to be effective in solving complex optimization problems. In this presentation, I will be discussing uh, the disadvantages, uh, variation of the method, and many more. By the end of this presentation, you will have a better understanding of how Newton's method works and how it can be applied to optimize complex functions. Let's get into it. Uh, this method help us to find the roots and optimize the function uh, uh, to optimize the very important functions in mathematics, science, and engineering. This problem can be challenging to solve analytically, especially for a complex function. If a function involves some e power function as well as some trigonometric function which has a complex derivative, because in this method we use a derivative to calculate the maximum or minimum value. If the function has a complex derivative, that can be very challenging us to find the root of that equation. If we won't be able to find the root of the equation, then we won't be able to get the ultimate solution of a problem and apply it into the real world. So to get a solution of a complex problem, we use this method. And so let's discuss about the advantages of this method. This method will help us to solve the nonlinear equations, which are very complex. When we go for an analytical way. This method help us to solve a nonlinear differential equation, nonlinear integral equation. The order of convergence is quadratic. Now let's see what is the order of convergence means. The order of convergence is a measure of how quickly an iterative numerical method converges to the exact solution. It provides information on how fast the error decreases as the number of iterations increases. Now, what is the order of convergence is quadratic means when the order of convergence of an iterative numerical method is said to be quadratic. It means that the method converges to the exact solution at a rate of approximately order of n square, where n is the distance from the current approximation to the exact solution. In this method, as I said, we use the iterative method. So, iterative method, uh, they like suppose our like what solution we have assumed, if it is far greater than or far a minimum from the our exact solution, there can be a lot of iteration. So if we apply this method using a computer, it will be very easy because computer can perform billions of operation in seconds. So it gives us a uh, is to find out the solution of a complex equation using this method. So now let's talk about the disadvantage. As I said, we use the first derivative of a function to find out the maximum or a minimum value. So if the function has a complicated derivative of, so that would be that would be a challenging thing for us to find the solution of that function, because we use the derivative to find the maximum or a minimum value. Now, the method requires a great and a sensitive attention regarding the choice of its approximation, because in Newton's Raphson method, first of all, the function f of x should be equal to 0. Now, to calculate the point on a curve, we assume x, root value x naught, that should be nearer to the exact solution. If it is far away from the exact solution or far lesser than the solution, then it will take a lots of iteration. So to perform those iteration, we will be needing a lot of time and a memory of a computer. So if the assumed answer is in lesser range or is approximate equal, then it will be easy to get the solution. In each iteration, we have to evaluate two quantities f of x and f dash x for some x. That is, for each iteration, we calculate f of x value as well as the f dash x value to draw a tangent to the curve. Like we are, as we are performing iteration, for each iteration we draw a tangent to the curve, and as like we are going further and further, this tangent will approach to the exact solution of the curve, and as like we perform the iteration, the error will be reducing and will be approaching the exact solution. So for performing each iteration, we need to calculate two values and then draw tangent. So it is a quite like a time taking thing. So that would be a disadvantages of Newton's method. Now uh, let's discuss about Newton's method. Let's consider a quadratic approximation of a function f of lambda at some point lambda is equal to lambda I. Now, as using the Taylor series on f of lambda, we can expand the function as f of lambda is equal to f of lambda I plus f dash of lambda into lambda minus lambda I divided by 1 factorial plus 1 by 2 f double dash of lambda I into lambda minus lambda I whole square. By setting the derivative of equation equal to 0, we'll be getting a minimum value of a function. So let's f dash of lambda uh, f of lambda plus f dash lambda I into lambda minus lambda is equal to 0. Here we are ignoring the f double dash derivative, as x should be like the error should be very less. So if lambda minus lambda would be quite lesser compared to f dash or f of lambda. Now as I have explained here, lambda it is improved the approximation as lambda I it plus 1 is equal to lambda I minus f dash of lambda divided by f double dash of lambda I. And now Newton's method for finding the roots using the Taylor series. Now let's assume some x naught initial approximate root of a function f of x is equal to 0. Now to get x1, let the it is a next root of the function. X1 would be x naught plus del x. So f of x is equal to 0. By applying the Taylor series on x1, we can write f of x naught plus del x is equal to f of x plus f dash of x naught del x plus O of del x power 2. So as all the terms which will involves the power of del x greater than 1, because del x is very small quantity, we can ignore all the quantity. Now we can write as above explained, x1 is equal to x naught plus del x. So we can write f of x1 is equal to f of x naught plus del x just by putting the value of x1 is equal to x naught plus del x equal to 0. Now f of x plus f dash of x del x is equal to 0. Now from the given equation, we can write del x is equal to minus f of x naught divided by f dash of x naught. Now let's find the value x naught, the value of x1. As we know, x1 is equal to x naught plus del x. So we can write x1 is equal to x naught minus f of x divided by f dash of x naught, keeping the value of del x in the x1 value. So we'll be getting the root of the equation. Now let's draw a triangle. Let's draw a tangent to the f of x curve. So to find, so we know the equation for passing a line through 2 points. Let's assume the another point is x comma y. Now the line passing through x naught comma f of x naught and y comma x would be y minus f of x naught is equal to f dash of x naught. F dash of x naught is the slope of f of x naught. So we can write the line equation as given here, f dash x naught into x minus x naught. Now to calculate the x value, we will set y is equal to 0. So by keeping y is equal to 0, we'll be getting x is equal to x naught minus f of x naught divided by f dash of x naught. So by generalizing the iterative formula, we can write x of k plus 1 is equal to x of k minus f of x of k divided by f dash of x k, where k will be k is equal to 0 to n. Now this is a graph where this line will be intersecting to x-axis here. The graph on y-axis, the y value is the graph, the y and x value are not exactly zero on a origin, so that's why the graph is not intersecting to the curve. So the point we have approximated is x naught. We have drawn a red tangent passing through the x naught and find out the x1 value, which will be nearer to the exact solution compared to the x naught. By performing such iteration, we as we are performing more and more iteration, we'll be approaching the minimum value, that is the root of the curve, which will be intersecting to the x line. Now finding a positive root, real root of cos x minus uh, x cube, cos x minus 3x square is equal to cos x minus x cube is equal to 0. Obtaining an initial approximation since cos x is less than equal to 0 for all x and for x greater than or x cube greater than or the positive 0 must lie this, the x must lie between 0 and 1. So let's take x naught is equal to 0.5. It is a approximation that we are assuming that our function cos x minus x cube having a solution 0.5. Now the solution, first we will compute the f dash x value to find the next solution, that is x1. So the derivative of f of x will be minus sin x minus 3x square. Now for first expression k is equal to 0. So x1 will be x naught minus f of x naught divided by f dash of x naught. Keeping the x naught value, will be getting x1 is equal to 1.1121. Now for second iteration, k is equal to 1, and putting the value of x1 in x1 in function, like that is x2 is equal to x1 minus f of x1 divided by f dash of x1, you'll be getting 0.90997 and so on. For last iteration, we got the value 0.8654. As you can see, for third iteration 4 and fifth iteration, the value of root is equal. So we can say that the approximate root of the curve is 0.8654 from the iterations. Now coming to the applications of the uh, Newton's method. This method helps us to find the roots of a equation. Find roots of a equation. Can be used to find the roots of a equation, which is useful in solving many engineering and scientific problems, especially when an exact solution cannot be obtained analytically. It is a fast and efficient method for finding roots of a equation, and it can converge to the root quickly. With good initial guesses. Nonlinear, it helps to do a nonlinear optimization to it is a effective method in solving nonlinear optimization problem, such such as minimizing or maximizing a function subject to constraints. It is commonly used in economics, physics, as I said in an introduction, and it can be used in image and signal processing too. Newton's method is used in signal processing applications such as image denoising, deblurring, and reconstruction of image. It can be also used in machine learning to learn various machine learning algorithms such as logistic regression and support vector machine machines to optimize the objective functions and find the optimal values of the model parameter. It can be used in a control system to optimize the control parameters and improve the system performance. Overall, we can see that Newton's method is a powerful optimization algorithm that has a wide range of applications in various fields. Uh, its effectiveness and efficiency make it a popular choice for solving complex optimization problems. Here, I have written a code for x cube minus x square plus 2, assuming the initial value, the root of the equation x naught is equal to minus 2, 0. It is a C++ language. I have commented what the function does here. That is using C++. You can see that. And the output value of a root is minus 1. That by seeing, we can see like if we go for a Analytical solution, the root of the equation will be one root of the equation will be minus one as well. So I'll keep minus one in the equation x cube. The cube of a minus one is minus one, and the square of minus one is one. So minus two minus one plus minus one will be minus two, and plus two is equal to zero. So you can say it is quite correct method, method. So thank you. I conclude here, and have a good day.